Okay, now let's look at some elastic collision problem. If you have a block A with mass 2 kg moves to the right with speed 4 meters per second and makes an elastic collision with block B and rest. After collision, block B moves to the right with speed of 2 meters per second. What is the mass of the block B and what is the velocity of A after collision? Okay. So the problem like that, initially we have block A and B. For A, mass M1 equals to 2 kilogram, right? B, let's call it M2. M2 is the quantity we want to find, mass of the block B. And what is the initial speed of block A? 4 meters per second. Let's call it V1 equals to 4 meters per second. And what is the initial speed for block B? 0. Okay, V2 equals to 0. And after collision, what we know is that after collision, the block B moves to the right with the speed 2 meters per second. So U2 equals to 2. And we also want to find for B what is the velocity of A after collision. So U1. Okay? So you can see the problem is simply we have two unknown quantities, M2 and U1. So first, generally speaking, it's a solvable problem, right? If you have two unknown quantities, you need two equations. Do I have two equations? Yes, it's elastic collision, so you have momentum conservation and kinetic energy conservation. Okay, so it's just about can you really solve this equation? And I think if you, at this point, you should be able to do that because anyway, it will involve the trick we just introduced here. Okay, how can we solve this kind of equation? So you have actually the general equation will be this and this, right? So in this case, V2 equals to 0. So actually you have M1 V1 equals to M1 U1 plus M2 U2. Okay, V2 equals to 0, so you don't have that term. Similarly, here you have 1/2 M1 V1 squared equals to 1/2 M2 U1 squared plus 1/2 M2 U2 squared. Okay, so that's the same thing because I have 0 velocity for V2, so I can simplify. Okay, any question here? And then again, you can cancel all the 1/2 here, so you don't have to worry about the 1/2. And to solve the two equations, what's the next trick you are going to do? Do you remember? It's behind this blackboard. Move some of the terms, so you are going to have
one object on one side.
And one side, another object on another side. So here, if M1 V1 minus M1 U1 equals to M2 U2. This is M1 V1 squared minus M. Okay, this is M1, right? Okay. So M1 U1 squared equals to M2 U2 squared. Okay? And then, if you use this equation, it becomes m1 v1 squared minus u1 squared equals to m2 u2 squared, right? The second equation. And the first equation becomes m1 v1 minus u1 equals to m2 u2, right? You factor out the mass and the left hand side. That's the reason you want to rearrange it this way. And then you divide the two equations. So m1 cancels m1, m2 cancels m2, right? And again, for this, you can apply that mathematical identity. So it becomes v1 plus u1, v1 minus u1 divided by v1 minus u1 equals to u2 squared divided by u2. So in this case, this cancels this. And for the right hand side, one of the u2 is cancelled. Okay, so you get v1 plus u1 equals to u2. So u1 equals to u2 minus v1. u2 is 2. What is v1? 4. So negative 2. Okay, by the way, I forgot to do one thing. I need to check the sign. This is positive to the right, it's okay. This is positive, okay, so that's correct. You get negative 2 meter per second. So u1 will go to this direction with 2 meter per second. Okay? Any question here? So I actually first solve the velocity. Any question here? And once you have the velocity, you can go back, substitute it into one of the equations there to calculate the mass. Which one should be the best one to use? The momentum conservation is simpler, right? Compared with the kinetic equation, energy equation. So you have m1 multiplied by v1 equals to m1 u1 plus m2 u2. So if you substitute all these numbers, m1 was it 2 multiplied by 4 equals to 2 multiplied by negative 2 plus m2 multiplied by 2. u2 is 2. So m2 equals to, okay, this is 8, this is 4. 8 plus 4 equals to m2. So m2 equals to 6 meter squared. So that's the mass. Okay? So for this kind of problem, usually, so if you understand one of them, all other kind of problem will be similar. We have all these quantities. We randomly pick 2 of them as unknown quantity. You just need to follow the trick to solve it. Okay. I can ask like a final velocity, 2 final velocity. I can ask 1 final velocity, 1 mass, or I can ask 2 initial velocity, or 1 initial velocity, 1 mass. Okay, it's just like this. Any question here? Okay, now I'm going to talk about the problem involving the changing mass. When we deal with the most of the problem, we have to make the mass as a constant. Not we have to. We always make the mass a constant. So when some objects are moving, the mass of that object will not change. Okay. And then we can use the Newton's second law, F equals to ma. So kind of we know that if mass doesn't change, then we do the force analysis, find the net force, and calculate the acceleration, and then calculate the velocity or something like that. Okay? So that's our common procedure. But there are problems we have to deal with changing mass, very mass. Okay, for example, the rocket problem. For the rocket, okay, there is a fast mass change because it will keep image the material, the material, okay, behind it. And sometimes, because the rockets, they have several different parts, they will keep dropping the back part, okay, to acquire larger velocity. You know that usually there are three parts, okay. They first drop this part, and then drop this part, and keep the top part. Or sometimes they even bound some small rocket here. They will also be dropped during the motion. So for the whole system, the mass, okay, so for this part, the mass keep changing, okay. And of course, another thing is that it's sent materials, okay, when it's moving. So the mass actually changed. Now, to solve this kind of problem, we have to extend our equation, the Newton's second law. Okay. In fact, it's not even extend. This is not the original form of the Newton's second law. Okay, when Isaac Newton proposed this law. Isaac Newton, when he proposed this law, he wrote it in a different way. You write it as this: F net equals to dP over dt. That's the original form of the Newton's second law. It simply says that the net force equals to the time rate of the momentum change. Okay. And we can see that this equivalent for if mass equals to a constant. We can see that equation is equivalent to this equation. Okay? So it will read F net, let's do one dimension, so we don't really need to worry about the direction. dP, okay, divided by dt. But P, let's think about one object with constant mass. So the momentum is simply mv, right? And if mass is a constant, so if mass is a constant, you can factor it out. So it becomes m dv over dt. But what is dv over dt? That's acceleration equals to ma. Okay. So actually, for constant mass, they are the same thing. But now let's see what happens if m is not a constant. If we change, then let's do the derivative. In this case, F net equals to dP over dt equals to dmv over dt. Now this time, both the mass and the velocity will be some function. So we know how to do the derivative for this, right? If you have z equals to like x, y, if you want to, some function equals to f, x, y, if you want to take the derivative, we have the rule, you keep one of them, take the derivative for another one, right? And then you keep another one, take the derivative of the first one, right? What's the name of this rule?
Product rule.
Quotient.
Quotient. We're multiplying it.
Okay, sorry, I didn't know what again. What's the rule?
Quotient rule.
Quotient rule.
That's the product rule, yeah, the quotient rule.
Product is product rule. Okay, so you get two terms. The first term is our normal term MA, right? So the first term is our normal term MA. The second term is, you can think about that. Okay, so it's some effective force due to the change in the mass. So it's dm over dt. So it depends on the mass change rate. Okay, thus it depends on the velocity change rate. So we have two terms, and that give you this equation, which can be applied to the rocket problem. The first, practical rocket is invented by Robert Goddard. He's an American, and I forgot the year. Maybe 20s or 30s, 1920s or 30s. I don't actually remember. It should be before the World War II. So that's the first one, a practical rocket. But the first rocket has been invented long time ago, in China. This guy called Wan Hu, he actually made some rocket like that. He found a lot of fire work, in his chair and launched it. That's the first rocket experiment. It's even a human carrying experiment. Himself was there and he was died. He died due to this experiment.
Oh, wow.
You can see, of course, there is no way you can survive after this kind of experiment. So that's in Yuan Dynasty. So it's in the. I have bad time to memorize the year. Maybe 1400, something like 1400, 1300. Many years ago. And because of this experiment, because he's pioneer of rocket science. So actually, one of the crater in Moon is named as Wan Hu. So this name. And in fact, Wan Hu is not even his real name. We don't really know his real name. Wan Hu is actually he's an officer of the military. So Wan Hu in Chinese means you are going to lead 10,000 soldiers. So he actually an important person. To lead 1,000 soldiers. Big orbit. It's also a interesting thing because so in the history, people always try to fly. So they made a lot of experiments to make it fly. Like they put some feather in the hand and jump from the mountain, and they die. But that's something inspired people finally invented airplane, rocket, all these things. And next class, we're going to discuss about the detail of the rocket problem. We want to calculate some quantity related to rockets. This calculation actually involves another important person, Tsiolkovsky. He's the father of the modern rocket, the theory part. He's from Russia. He's a Russian.
Yeah, you don't say.
So that's it. Next time we are going to